Thanks for the introduction. So this talk is about correlation, intractability, and the SNARGs from sub-exponential DDH. I'm Zhengzhong Jin, and this work is joint with Arka, Choudhuri, Sanjam, Garg, Abhishek, Jain, and Jiaheng, Zhang. So let me first recall what is SNARG. So SNARG means succinct non-interactive argument. So it is a proof system where it allows a prover to convince a verifier that some machine M runs on some input X where output 1 within T steps. And here, the machine M is some deterministic or non-deterministic Turing machine. And we require the proof size to be short and the verification time to be much faster than this T. And we also require the following completeness and soundness. For completeness, we require if M of X equals to 1, then the honestly generated proof will always be accepted. And for the soundness, we require that if M of X doesn't equals to 1 within T steps, then any efficiently generated proof should be always rejected. So an important subclass of NP is called a batch NP. And in a SNARG for batch NP, the prover tries to convince the verifier that a batch of K statements are all true NP statements in a single message. And we require the proof size of such a proof to grow with one of the NP witness. And so previously, this subclass of NP is known as the complete problem towards building SNARG for P, in the sense that if you know how to build SNARGs for batch NP, then we can compile it generically to obtain SNARG for P. And some similar notion of this batch proof was also considered before in the context of digital signatures and the interactive proofs, such as multi-signatures or interactive batch proofs. So previously, we know how to build SNARGs for P or batch NP from standard cryptographic assumption or well-studied cryptographic assumption. And we know how to build SNARG for P or batch NP from learning with error assumption. And recently, the work by Waters and Wu constructed SNARGs for P and batch NP from bilinear maps. And also there is another work constructed those SNARGs from Diffie Hellman assumption and the quadratic reciprocity assumption. So the latter two works, they are stronger. So the assumptions they use are stronger than the Diffie Hellman assumption on non-pairing groups. So what is this Diffie Hellman assumption? So the Diffie Hellman assumption is defined as follows. So it assumes that given two random group elements, G to the A and G to the B, it is hard to distinguish this G to the AB from a random group element. And this assumption was firstly used to achieve public key encryption, public key cryptography for the first time. So in this work, we studied the following question. Can we build SNARGs for P and batch NP from decisional Diffie Hellman from the Diffie Hellman assumption? So answering this question can help us understand the power of Diffie Hellman assumption. So we have a Diffie Hellman assumption and other cryptographic assumptions. So it's interesting to understand for the cryptographic functionalities that can be achieved by lattice assumption and the bilinear map assumption, can we also achieve the same functionality from the Diffie Hellman assumption? Or is there a gap between Diffie Hellman assumption and these other cryptographic assumptions? So recent years, such a gap becomes narrower and narrower. So in the context of multi-party computation, the work of Boyle et al. Constructed a succinct secure computation from this Diffie Hellman assumption. And in the context of advanced encryption schemes, the work by Dottin and Garg constructed identity-based encryption from Diffie Hellman assumption. And recently, in the joint work with Jain, we constructed non-interactive zero-knowledge proof systems from sub-exponential hardness of Diffie Hellman. So in this work, our focus is on SNARGs. So we try to understand whether such gap between Diffie Hellman assumption and other cryptographic assumption exists or not in the context of SNARGs. So can we build SNARGs from Diffie Hellman assumption? And here is our result. So we constructed the SNARGs for P and batch NP from the sub-exponential hardness of Diffie Hellman assumption. So the sub-exponential Diffie Hellman assumption in our work is defined as follows. We assume that there exists a constant C such that for any adversary that runs in some slightly super polynomial time, which is lambda to the order of log lambda to the cube time, it can still not distinguish DDH tuple and a random tuple with advantage more than some sub-exponential amount. So here, in this sub-exponential DDH assumption, we not only require the advantage to be a sub-exponential amount, we also allow the distinguisher to run in some slightly super polynomial time.
Why are we choosing this particular log lambda cube? I mean, is there something?
Yes, you will see it later. So we will use some complexity leveraging. So as a concurrent work, the work by Kalai et al., they also construct SNARGs for all of bounded depth deterministic computation from sub-exponential DDH assumption.
So what's the comparison? You can do SNARGs for P.
Yeah, so
you do SNARGs for bounded density.
Yes. So in their work, they can work for bounded depth, so deterministic computation. Essentially, they apply Fiat-Shamir to Jiaheng. So a key ingredient in our work is a construction of a correlation-intractable hash. So let me first recall what is correlation-intractable hash. So we say a hash family is correlation-intractable for a relation class R. If for any relation R in this relation class, for any polynomial time adversary, given the hash key sampled by some key Jain algorithm, it is hard for this adversary to find some input X such that the input and output pair of this hash function under this point X satisfy this relation. And so this is the definition of correlation-intractable hash. So this kind of hash function has found many applications recently, such as showing the Cont examples to zero knowledge. And it was also used to build non-interactive zero knowledge proof systems. And it was used to construct verifiable delay functions. And it was also used to show the complexity of p-part hardness, or the hardness of Nash equilibrium. And recently, it was also used to build error-correcting codes. So why we care about such a special hash function? So we will use this correlation-intractable hash to instantiate the Fiat-Shamir paradigm and then build the SNARGs. So recall that the Fiat-Shamir paradigm starts with some interactive protocol where all of the wirefires message are uniform random strings. So here is an example of a 3-round interactive protocol where the prover sends the first message X and the verifier sends a uniform random Y in the second round. And then the prover proceeds to the third round Z. If you apply the Fiat-Shamir using this correlation-intractable hash, we're going to, so the idea is we are going to replace the second message Y with the hash of the first message X. And to prove the security of this Fiat-Shamir paradigm, the idea is to first define what is a bad challenge Y. So we say the second message Y is bad if with respect to the first message, with respect to a fixed first message X, if it gives the prover a chance to cheat. So this is just an intuitive description. And more precisely, it means that we need to define a bad relation. And this relation contains all the pairs of all the pairs of X and Y, such that there exists a third round message that can make the protocol transcript start with X and Y be accepted by the verifier for any fixed false statement. So once we have this bad relation, we can then use the correlation intractability of this hash function to argue the security of Fiat-Shamir. So in this work, we care about a particular relation, and this relation is called the verifiable product relation. So this relation is motivated by the parallel repetition of interactive protocols. So suppose we want to apply Fiat-Shamir to parallel repetition of some interactive protocol. For example, here is a parallel repetition of a 3-round interactive protocol. So here we have T parallel repetitions. And we can denote the collection of all the first message as X. And note that if we consider the bad relation of this parallel repetition, then it satisfies an additional structure. Because intuitively, for any fixed X, if the concatenation of Y1 and YT allows the prover has the chance to cheat, then this means that so in order to have the prover to cheat for this parallel repetition, the prover need to be succeed at each of the parallel repetition. So for any fixed X, if we denote the bad X as the collection of all the second message that allows the prover to cheat, then this bad X has a product structure. So this bad X can be represented as the set product of bad 1 to bad T, where each bad I is the bad relation for the ith parallel repetition of this interactive protocol. And so this verifiable product relation just further require for each of the bad relation, this bad I, there exists a circuit CI such that this bad I is just the NP relation defined by this CI. And yeah.
Can we always have verifiability? It's not obvious.
Yeah, good question. So in fact, to achieve this verifiability, you need to embed some trapdoor in this interactive protocol. You need to use some CRS in this interactive protocol, and using this trapdoor, you can extract some information from this X, and then you can compute this. You can check whether a given challenge is bad or not.
But that seems specific to some construction.
Yes, it's specific to some construction.
To your construction or all construction?
Not all construction. So in our construction, we take such a protocol.
Okay.
So sorry, what does the circuit CI depend upon? It doesn't depend upon Xi and Yi, right?
Yeah, CI doesn't depend on X or Y. CI is just, it only depends on your protocol.
So why is there a different CI for every I?
Oh, so yes, so each CI, so for example, the C1 is defined with respect to the first parallel repetition, and C2 is only defined for the second parallel repetition. So for each parallel repetition, there is a C. Okay, and in the previous work by Homegrown et al., they constructed a CIH for efficiently verifiable product relations from with arrows. And the efficiently verifiable product relation is just a verifiable product relation where this circuit CI is a polynomial circuit. So, and this is very useful because without a loss of generality, for any NP relation, almost for any NP relation, you can always do some parallel repetition. So, and indeed, this is how we achieve our result in one of our previous work with Choudhuri and Jain. Yes.
Bad bars, right?
Yeah.
So, okay, you find the part distribution, but what does it mean that you verify this part distribution? You verify that there's something, try to prove something is correct, but there's no bad thing.
Oh, right. So here this bad relation is used to prove the security of Fiat-Shamir. So to prove the security of Fiat-Shamir, we need to show if the statement is false, then any cheating proof should be rejected. So any proof should be rejected. And here this So, and to show this, the idea is, suppose there is some accepting proof, then this accepting proof must satisfy the condition that this beta equals to the hash of alpha, and this will contradict this correlation intractability for this bad relation, because right. So CI need to be a polynomial size circuit. It needs to be efficiently computable. So in their work, they handle any efficiently computable circuit. Yes. Yeah. In fact, you also need to be sparse.
What needs to be the formal condition?
So the formal condition is so you can think so the efficiency of such a hash function is almost the same as the parallel repetition of interactive protocol without this. It's almost the same as the in the information theoretical setting, in the interactive setting. I mean, so for any interactive protocol, you can do parallel repetition to amplify its soundness, and the amount of interaction, the amount of parallel repetition you need using this hash function is almost the same as the original. It's almost the same as the number of parallel repetition you need in the original interactive setting.
So let me ask you, can CI is polynomial time? CI needs to be a sparse relation.
Yeah.
Can all the YIs just be negligibly sparse, or it has some
Yeah.
additional structure?
Yeah. So in fact, it's you can think if the sparsity is alpha, then you may need some poly 1 over alpha number of parallel repetition.
Then why doesn't that mean you just have correlation intractable hash for arbitrary sparse relation?
So you need because you cannot prove soundness for in the interactive setting if your soundness error is too bad.
I understand that there needs the parallel repetition, but
So what you can do is start with the relation, do parallel repetition, sparsify, sort of, and then you can apply this.
The original circuit doesn't need to be sparse.
The relation needs to be sparse.
The relation.
Yes.
yeah, I'm asking that if I even just look at the one column, and he said, so if the CI only has the condition of being efficient and negligibly sparse, it sounds like a general correlation intractable hash function to me.
Not negligibly sparse.
And
I'm asking.
So I think you need T to be sufficiently large, right? Like you don't do it for T equals 1.
Yeah, if you start with a single column, and T needs to be sufficiently large because a single column doesn't have large enough correctness. Doesn't have large enough. It doesn't have very large soundness error. Right? And does that translate into some conditional CI for which you can build?
yeah, so I mean, I think it's easier to think that in perspective of trying to apply this CI in order to do Fiat-Shamir to an interactive proof. What we're saying here is take the interactive proof, apply parallel repetition to it. You need to do one extra step of specification, and then you can use. Yeah, as long as the
challenge space in one repetition is not super large, right? I mean, that's why collapsing it to T is equal to 1 case will not capture zero relations.
Somehow always in my mind is that for every, if I look at single column, for every first message, I have only a few bad challenge. And only for product combination of a few bad challenge, then you can build correlation intractable hash. But to me, that means there is some condition on, it's not that we build correlation intractable hash for arbitrary.
No, so think about like Blum's zero knowledge, right? There's two possible challenges only.
Yeah. So
For one column, it's nothing, right? Like you can't get sound. It's just like they're just two possible challenges. One of them is good, one is bad.
Yeah, I'm not confused about the fact that you need parallel repetition. For sure, you need it. I'm asking that we don't have general correlation intractable hash for an arbitrary interactive proof. So it means I don't have correlation intractable hash for arbitrary relation. this is a special kind of relation, right? And I'm just asking that what's that the specialty? If I have no conditional CI at all,
The
then
efficiently
I get the
verifiable,
general correlation.
the efficiently verifiable makes it hard to extend this to general because you should be able to efficiently test if the challenge is bad.
I see.
So the sparsity, like if the number of bad challenges divided by the size of the challenge space will determine how many times you need to parallel repeat.
I see. Only that part is different. Okay.
That's suffice, under general relation, you can sort of reduce to this case. It doesn't give you CI for general relation, but you can do Fiat-Shamir.
So let's continue. So this can handle many in fact, so essentially it can almost handle all NP relations. Because for any NP relation, you can always do this parallel repetition. So, and this is indeed how we achieve our result in our previous work joined with Choudhuri and Jain. So in that work, we first built this interactive protocol for batch NP, and then we applied the Fiat-Shamir using such a CIH from the work by Holmgren et al. Then we compiled to build a SNARG for batch NP. But in this work, since our focus is to build SNARGs from Diffie Hellman assumption, so we cannot use this lattice assumption anymore. So can we build this CIH for verifiable product relations from Diffie Hellman assumption? So suppose we can achieve this, then we can start with some interactive protocol for batch NP from Diffie Hellman assumption. Then we apply this CIH for verifiable product relation from Diffie Hellman assumption, and then we can build SNARGs for batch NP from DDH. And then we can compile it generically to obtain SNARGs for P from DDH. So that's the high-level overview. So, and here is our intermediate result. So in this work, we constructed this correlation-intractable hash for TC0 verifiable product relation for sub-exponential DDH. And in our construction, for any input length n, the running time of our hash function is a slightly super polynomial in n. So the running time is n to the order of log log n. So you can think to make this running time a polynomial, we need to restrict the input length to some small sub polynomial in lambda. In this way, we can obtain a polynomial running time. So in the rest of this talk, I'm going to show you how to build this correlation-intractable hash for TC0 verifiable product relations from sub-exponential DDH. Oh, TC0. So yeah, I will show you. Yeah, maybe I will explain later. But before that, so let me first show you some background about the CI hash. So let me first show you how to build a CIH for searchable relations. So what is searchable relation? So we say a relation R is searchable if there exists an efficient function f such that this R is completely characterized by this function f. So this relation R will just contain the input-output pairs of this function f for any input x. And here I'm going to show you a very simple construction of CIH for searchable relations from circular secure fully homomorphic encryption. So let FHE be some circular secure fully homomorphic encryption scheme. So the hash function we construct has the following hash key. So the hash key just consists of the fully homomorphic encryption of the description of this function f. And we set this ciphertext as a hash key. So to compute a hash, the idea is to for any input x, we're going to homomorphically evaluate the universal circuit with x hardwired in it. And in this way, we can compute a ciphertext which is a ciphertext of f of x. And the next, by assuming circular secure FHE, we can homomorphically decrypt this ciphertext. So we can obtain a FHE encryption of the decryption of fx. And the hash value is set as the FHE encryption of the decryption of f of x plus some shift. So let's say we plus some vector of ones. This is the hash value. So this is the construction in the work by Kennedy et al. And the next, I'm going to show you why this construction is correlation intractable for this function. Yeah. So you.
What is the decryption algorithm?
So decryption algorithm has the secret key hardware. So the construction also assumes circular. Yes. So it internally decrypt this. It treats this f of x as some ciphertext and decrypt it.
Decryption of fx, you just mean fx there. It's the decryption of FHE of fx. It's just fx.
So it's so
FHE, I mean encryption of it. Homomorphic decryption of encryption of it.
Okay, so the decryption of the encryption.
No, it's just FX.
Okay, so
He has his decryption step first, then he does decryption of that. So you do see FX as a ciphertext for some reason, and he decrypts that, gets some bizarre thing, and then he encrypts and decrypts that. Yes. So in other words, this is the instead of that second rule, isn't that just the decryption of it from FX?
yeah. So you decrypt the f of x under the hood.
Why do you decrypt and then?
Oh, yeah. So it's used to show the correlation intractability. So I will show you this construction. So the construction looks like this, and I will show you it satisfies correlation intractability. So suppose I was very confined some input x such that the input-output pairs under this hash function h satisfies this relation. Then this means that since this relation is searchable, this means that this hash of x equals to f of x. And if we take in the construction of this hash function, then this means this FHE encryption of the decryption of f of x plus this shift equals to f of x. So if you apply the decryption on both sides, then you obtain this decryption of f of x plus this shift equals to the decryption of f of x. And you can cancel this decryption on both sides. Then you will reach a contradiction. So now we show that if suppose some adversary can find some input x, can break the correlation intractability, then we can find some contradiction. In this way, we prove the correlation intractability. So this is how the work by Kennedy et al. Constructs this CIH for searchable relations. And later, in the beautiful work by
no, just that they're different,
Just
right?
the contract.
Anything non-zero, right? Anything sacrosanct?
Yes. Yeah. Anything non-zero. So, and later, by the beautiful work of Piker and Jiaheng, they constructed this CIH from for searchable relations, for efficiently searchable relations from any from the plain learning with error assumptions. And but in this work, our focus is on the Diffie Hellman assumption. So can we build this CIH from Diffie Hellman assumption? From Diffie Hellman assumption, previously, we only know how to build CIH from approximate constant degree polynomial from Diffie Hellman assumption. And this is by the work of Braxky et al. And the main challenge here towards building CIH from DDH for more general circuit is that the Diffie Hellman assumption is defined in a cyclic group. So in a cyclic group, it seems that the only homomorphism we can do is the linear homomorphism. Yeah, question?
DDH also needs
Good. So that paper, to build an ZIP, you also need LPM. But to build this CIH, you only need a Diffie Hellman assumption. So the main challenge is that in the Diffie Hellman assumption is defined in a cyclic group, and in a cyclic group, we only know how to do linear homomorphism. It seems that we only know linear homomorphism. So, and this is very different from the lattice assumption because based on lattice, we can build a fully homomorphic encryption. And to overcome this barrier, so one of the recent work joined with Jain, we constructed a CIH for TC0 searchable relations from sub-exponential DDH. And the key idea is to use more interaction to emulate this Fourier homomorphism. So we first relax this hash function. So here is an overview of our construction. So we first relax this hash function to some interactive hashing protocol, where we allow the hash algorithm and the key generation algorithm to interact in multiple rounds in back and forth. And as you can imagine, in any 2 rounds of this interactive protocol, we can compute some linear function. And then we compose these linear functions sequentially to obtain a more complicated function. And then we use a round collapsing technique to compress this interactive hashing protocol to obtain a hash function without any interaction. So here we stop at the TC0 because in this round compression technique, we need to use some complexity leveraging. And if we use too many complexity leveraging, then we cannot rely on sub-exponential hardness of DDH. So if you want to know more details, we can discuss later. In this work, our goal is to build a CIH for verifiable product relations. And so let me first recall what is verifiable product relation. So for such a relation, for any given input x, the bed of x can be decomposed as the product of several sets. And our first observation is that if each bed I only contains one element, and the challenge space for each bed I is a polynomial, then indeed I can enumerate every y in the challenge space and check whether it is bad. And if it is bad, I just output it. So in this way, I can build a series of functions from f1 to ft, where each function will output the unique bed elements in this bed I. Now this verifiable product relation is essentially a searchable relation, because I can just concatenate this f1 to ft together to obtain a function, to obtain an efficient function. So here we crucially rely on 2 points. So one is this each bed I only contains one element, and the second is the size of this challenge space is a polynomial. So how about bad challenge? How about multiple bad challenges? So for any relation R.
Sorry, so
yeah.
Can you go back?
Yeah.
So I understand it's searchable. And am I supposed to be happy now, or I don't understand the connection to TC1 or anything?
Yes, good question. So in fact, we also so to make this searchable, in fact, to apply our CIH for TC0 searchable relation, we also require this f1 to ft to be in TC0. But and to make that possible, we need to make the verification circuit for each bed I to be a TC0 circuit. So once that circuit is in TC0, this enumeration process is also in TC0, because you can enumerate all possible y in parallel. Good question. So, right. So, and so how do we handle these multiple bad challenges? So for any relation R, our idea is to divide the challenge space y as several components from y1 to yd. So you can imagine if this y is 0, 1 to m, let's say. So if y is the strings of length m, then each yi is a binary string of length. So each yi contains all the binary strings of length m divided by d. So in this way, we can divide this challenge space evenly to several small challenge space. And the idea is that by this dividing process, maybe we can also divide the bad challenges among this y1 to yd, so that they could be unique. So let's take another view of this dividing process. Yeah. Sorry. Good. So initially we have challenge space y, and and next I'm going to compute each element in the component of y in this y1 to yd. So in the first step, I'm going to compute y1, and the next I'm going to compute the component of y in y2, so on and so forth. So let's first focus on the first step. So computer is component in y1 is essentially dividing the whole challenge space into the size of capital Y1 subsets. And then a value in Y1, a value in this component of capital Y1 essentially is an index for this subset. So Y1 will choose one subset. And the computation of the component of Y in Y2 is essentially dividing this subset further to capital Y2 parts. And then we take one parts from them. And this part is indexed by Y2, and so on and so forth. So, and the hope is that in this dividing process, we hope the bad challenges will spread among different subsets. So that, and here, our key observation is that at most one subset will contain more than half of the bad challenges. And this way we can obtain uniqueness. So essentially now we can reduce any bad relation to the unique bad challenge case and apply our proposed construction. So that's the initial idea. Yeah.
So suppose there were two bad challenges in each of the sets from the previous, for each of the parallel repetitions.
Yes.
What happens?
So
overall, there's 2 to the t bad challenges. That's too many.
So you mean there are 2 bad challenges in total?
No, there are 2 for each. You're doing t repetitions.
Yes.
And in each of the repetitions, there are 2 possible bad challenges.
Yes.
So 2 to the t in total bad challenges. So
yes.
What happens here?
So here, I'm going to divide the whole challenge space. I'm going to first divide the whole challenge space to capital Y1 subsets. And I'm going to select one of the subset. And I continue to divide it and continue to divide it to Y2 subsets. And I'm going to choose one.
Original challenge space, not the.
Yeah, so guys, this slide is not for the product setting yet. This is even just considering the setting that suppose you had a relation, right? Non-product relation with let's say some number of bad challenges and some challenge space.
Mm-hmm.
If you could handle searchable relations, now how can you go to multiple bad challenges? So just for the single repetition setting, he's first describing an idea which then extends to the parallel case.
So there'll be only 2 dots in this setting for your example. And you argue that there's only one of these slices which will have more than 1 dot at most. So let's say 3 dots. There'll be at most 1 slice which will have 2 dots.
Okay. One quick question. Is Y1 a random subset or is there a niceness relationship? Like, is it a linear subset or?
Good question. So in fact, good question. So we don't need it to have any structures. We just divide them in any way. So key observation is that in this dividing process, each time when we divide this challenge space, there are at most 1 subset that contains more than half of the number of bad challenges. So in this way, we can obtain uniqueness. So, so next, I'm going to show you how to use this idea to build a CIH function. So our idea is to divide the challenge space to this Y1 to YD. And now I'm going to first recall how this.
The argument that you hope you are choosing one of the subsets which is not the majority subset every time, and therefore you end up with only 1 dot. Is that the?
So the argument is that so suppose there are 2 subsets that contains more than half of the number of bad challenges. Then in total, the number of bad challenges is more than 1 fraction.
I get that, but what if you choose the one subset which has more than half of the bad challenges?
Good question. So you will see later. You will see in the next slide. So So our construction, we will construct this CIH as follows. So let's first recall how CIH is used in the Fiat-Shamir paradigm. So let's say we have some interactive protocol where the prover sends the first message X, and then the verifier sends a random challenge Y. So now instead of sending this Y directly, we're going to replace it with some interactive protocol where the verifier first sends the first component, first sample a component in Y1, and then second sample a second component in Y2, so on and so forth. And finally, we concatenate all of those challenges together to obtain the challenge Y. So now you may wonder, maybe there is no difference between this and the original interactive protocol by directly send this challenge Y. So the difference is that if we apply the Fiat-Shamir to this interactive protocol, then we obtain this iterative construction of CIH. So to apply Fiat-Shamir to it, we are going to first compute Y1 as the hash of X, and this is some hash function H1, and then we compute H2. We compute Y2 as the hash of X and Y1, and so on and so forth. So at any step, Yi is computed as the hash of X and Y1 to Yi-1. So, and our goal is to show that for each, our goal is to show that we are going to define a unique bad challenge for each Yi. Then we can use HK. We can instantiate this hash function Hi as the CIH for unique bad challenge. Then we can argue the correlation intractability of this construction. So for your question, so the idea is we can catch that case. We can catch that case when you really choose the Yi, when you really choose a better Yi by using the correlation intractability of some Hi in this construction. Yeah. So I think I run out of the time, and this is the this is the high level idea of the construction. There are many challenges in this work. For example, yeah. So.
Where's started saying you're going to where does this all?
What you mean? Where does it go?
In general, but what's the key thing that makes this unique work with Diffie Hellman rather than other assumptions?
Good. So for Diffie Hellman, we don't have this homomorphism such as lattice. So for Diffie Hellman, we only know how to use linear homomorphism, and that restricts us to construct the CIH for TC0 circuit. So that's restrict us to. So we can only construct the CIH for TC0 searchable relations, and yeah. So the previous construction of this homogram at all, they need to rely on least recoverable code. So that construction need to use CIH for searchable relations. It's called the least recoverable code.
So if someone come up with least recoverable codes with decoding in TC0, that would be.
Yes. Yeah. Yes, that would be an alternative.
Your construction, can you use it also in LWE or?
Yeah, I think so. I think it also applies to LWE.
Okay, let's thank the speaker. Guys, sit up and take some more questions.